Okay, so now what I would like to discuss the different ansatz that can be used when you want to build a machine learning wave function. And so maybe as a just a kind of a reminder, the simplest ansatz somehow that you can do is just to consider a slider determinant. And the thing is that all the ansatz were built on a slider determinant. So a slider determinant, just as a reminder, is just that you consider the determinant of one-body orbitals like this. So phi I of Rj. And we never use variational Monte Carlo for this kind of ansatz, just because of the first-order optimality condition. But in principle, it could be used as an ansatz. And then here, the main question is how you parameterize the orbitals. And so usually you take some basis, and then you optimize on the basis. Okay, and so so that's kind of ansatz 0. The first ansatz, so this has the slider determinant has the correct antisymmetry. And so now we want to kind of enrich the space of wave functions, but we don't want to lose the antisymmetry of the wave function. So a way to do so is just to add a symmetric function in front of the slider determinant. And so this is called the slider-Jastrow wave function. And so here the idea is just to multiply the wave function. So Rn, R1, Rn. So maybe should I? Sorry, I will try to keep notation with x. So x1, xn, xj, x1, xn, and so this is basically a slider determinant. So determinant psi xj, and we multiply by a symmetric function, which is often written as an exponential g of x1 to xn. And so this is called the Jastrow factor. And this is something that is really quite old already. So it was, sorry, I will write it again. So it's exponential minus j of x1, xn. So it's exponential minus j x1, xn, determinant by I xj. And so this is the Jastrow factor. And this was introduced by Jastrow in 1955. Okay, and here J is a symmetric function. Because if you have a symmetric function, then if you permute the variables, you get the antisymmetry from here, and the the symmetric function doesn't destroy this antisymmetry. Okay, and so here one of the main idea that you can build on all what I presented for the interatomic potential is that here you have a fully symmetric function that depends on n variables. So instead of the atomic position, you have now the electronic positions, but then you can do exactly the same as before. So you can pick your favorite interatomic potential, and you can put it here as a Jastrow factor somehow. So you can use the descriptors, the functional forms that I presented, put it here, and then say that the wave function is parameterized by those parameters. Okay, and so somehow a first Jastrow factor that you can use is just so a jx1 xn would be some kind of looking at pairwise interaction, some function u of x I minus xj or something like that. So that would be a possibility. Yes.
Here we don't care about the normalization since it was taken into account in the RAD evaluation.
Yes, exactly. Yeah. Okay, and so one of the main problem with this on that is that it is not complete. So we know that Slater determinants are not complete in the sense that they don't generate the full space of wave functions. But in fact, so adding a Jastrow factor is not enough to make this complete. And hand-wavy explanation is that is related to the nodes of the wave functions. So the nodes of the wave functions are given basically by what you have in the Slater determinant, and they cannot be changed by the Jastrow factor. And so if you fix the orbitals that you use here, you cannot generate all the nodes that you would want by just adding a Jastrow factor. Okay, so then let's say the other most typical ansatz is called the backflow ansatz. So so this is also something that was proposed in the 50s by Feynman and Cohen. In 1956, so really just 1 year after Jastrow's paper. And so here, the idea is to propose the generalized Slater determinant. And generalized in the sense that the orbitals will not depend on a single electron, so a single variable, but will depend on all the variables. So the one way to write this is to say that the wave function psi theta x1 to xn is the determinant of phi I. So we still have n orbitals, but then these orbitals depends on the xj and all, the collection of all other variables. And here, if we want to keep the antisymmetry of the wave function, we need these orbitals to be symmetric with respect to the exchange of the other orbital, the other particles here. So the orbitals have to be invariant with respect to permutations within the set of other variables. And this is shown to be complete. So there is a paper by Hutter in 2020, which proves this. Yes.
Invariant in this sense means symmetric.
Yes. Yes. Symmetric. It means that, yeah, if we switch two particles, then the value of the function doesn't change. And sometimes, so this, so I would say this is kind of the more generic definition for this, and sometimes it is presented as some kind of change of variables. So is somehow you say that you define Rj bar, which is Rj plus some kind of sum k not j of some function Rj minus R. Sorry, I'm on R again. Xj minus xi times xk. And then you say that you replace the orbitals phi I xj by phi I xj bar. So this is an example of something that can be proposed. So here, this is a specific choice for this generalized orbital.
You mean xj minus sk?
Yes. Thank you. And here, eta is some kind of correlation function. And so here we would, I mean, this would be somehow like a two-body extension of the orbitals somehow, because here we only consider like pairwise interactions. Yes.
Basically, I think it's similar to the explicit correlated function, so something like it.
Something like that. You kind of infer that the dependency on the variables that you should put in should look like something like this. And then you can say, okay, there is a correlation function, and I only learn this correlation function.
But if you limit yourself to this form, it's not complete.
No. In this form, it wouldn't be complete. Yeah. If you want something complete, then you need really to consider all, so a single Slater determinant, but with orbitals that depend on n variables. And with this, basically, somehow you can capture all possible nodes of the wave function. Okay, and so the last ansatz, which is really just a combination of the two, is to put a backflow ansatz plus Jastrow plus Jastrow. So in that case, the parametrization for the wave function is so exponential minus j of x1 to xn times the determinant of phi I xj x k not j. And so here you would have to parameterize both the Jastrow factor and the orbitals in some way. And somehow from there you can do all the cooking that you want, in the sense that you can also consider linear combinations of slider determinants. You can this also works. So you can kind of combine all the ingredients. And the idea is that at the end you just want a wave function which will be not too difficult to train. So somehow for which you can minimize the energy reasonably well. Yes.
But the factor on that is already complete.
Yes.
What is the interest of combining it with just?
Yes, so that's a good question, and I think the reason the reason I mentioned that is that people do that in practice, and so I think the reason is that the way you parameterize the orbitals may not be complete, in the sense that, for example, I am assuming that if you only use like two-body contributions, then you're not complete, and so somehow including on top of that a Jastrow factor will make you gain some accuracy. So that's like more like a practical issue that if in practice you want a wave function that is correctly approximated, then you do whatever you can. So and similarly, I mean, if you say one is sufficient, then why use like several slider determinants? The reason is that then you can somehow improve the fitting or accelerate the convergence of the fitting. Okay, and so now, yes.
Like the whole wave function be satisfied with fast conditions or something like that.
So that's also something that you can put in explicitly, yeah. Yeah. And that's also something that, that in practice is used. Like if you know, yeah. I think in the Paulinet they actually put the kind of the cusp condition explicitly in the Jastrow factor, and yeah. I mean, I think in general the message is often that if you know explicitly something that will happen, you are better putting it in your model if it doesn't increase the computational cost too much. Okay, so now I would like to present a little bit the Paulinet. So there have been quite a few methods that have been proposed recently, and so I will mostly focus on Paulinet and Ferminet, but I know that there are many other possibilities around. You had a question?
Are they doing like full electron calculation, or they have like significant?
I think they do all electron calculations. Okay, so the Paulinet so has been proposed in 2020. So by Herman and co-authors. So the paper is called Deep Neural Network Solution of Electronic Schrödinger Equation. And so here, they put in the wave function the physical constraints, so antisymmetry, and they actually also put, so as you asked, the electron-electron cusps in the wave function. So here, what they do is that they do Jastrow style ansatz. I mean, they do Jastrow plus backflow. And to give you a rough idea of what they do, so in the first paper, so I'm sure that has been improved after that, but in the first paper, they do systems with up to 30 electrons. And the asymptotic scaling of the method is n to the 4. Okay, and yeah, okay, so let me try to write down the parametrization. So so somehow, as for the message passing neural network, we quickly go into big formulas. But so here, so we have basically the Jastrow factor, which is composed of 2 terms. So some function C, and then some Jastrow theta 1 x1 xn. And okay, so I will write down the whole thing and then explain a little bit. So here, theta 2p, ji x x1 xn. Okay, so here, so that's a big Jastrow factor, and so here the C is for I'm assuming for the cusp condition and something that is explicit, let's say. And then they have a Jastrow factor here, and so this Jastrow factor is written as a neural network. And the idea is that it's based on the message passing neural network SNET. So basically everything that is symmetric is parameterized as a message passing neural network. And so then you have a combination of things. And so so another thing to note is that they use up to p determinants. So they don't only have one determinant, they have a collection of them, and then they sum over them. And so the last thing to see is how this function is parameterized. And so these pi theta 2 p ji of x1 xn is basically the product of a function that depends on our xi times a second function which depends on xk k not I. No, actually, they don't say that. They seem to say that it depends on everything. No, see, so this should be okay. So here I'm not sure, but I would say that it depends on the xk where k is not j. And so here what you have Okay, and so what they say is that in terms of to ensure the permutation invariance in the antisymmetry in the end, the Jastrow factor is fully symmetric, and then this actually is, so there is a collection of such functions, and it is equivariant to permutation. Yes. Thank you. So here, this should be equivariant with respect to permutation, and with this, it should be satisfied that the overall thing is, yes.
Your books by J, these are like even from the beginning.
So these, I guess, yes, yeah, exactly. So what they do is that they first run some multi-reference artifact to have several determinants, and then that's the orbitals that they use here, and so those are fixed, and then the things to learn somehow are these J theta 1 and the F theta 2. So that's the two, I mean, that's where all the parameters come from.
Your backflow here.
No, it's here, the backflow.
No,
Oh, it's not a backflow in, I mean, it's some kind of generalized backflow. It's not directly this kind of transform. It's just by backflow, I mean that here the orbitals depend on all the particles. Yeah, I mean, the backflow transform was originally introduced as this kind of transform, but somehow this, yeah, saying that the orbitals depend on the one particle and the others kind of as a collection is also, I mean, it's also called by in this paper backflow transform.
the S theta 2 is written as a neural network.
Yeah, so it's based on SNET, so a message passing neural network.
So the same kind of the.
Yes. So kind of SNET.
Different for different eyes, no, it's the same F theta for all their eyes.
Okay, sorry. This should be no, that should be J somehow, but then there is no I. Oh yeah, the I is in here. Let me check.
Nothing is using here.
Nothing is using P. P is here. P is because you have several determinants. Yes, okay. So basically it's everywhere, I would say. Because those are, so here you would have this and you would have this. Yeah, you select the orbitals, so those are given by a pre-computation, and then you only fit the kind of the remaining. And it also, I mean, it's expected that it improves the, I mean, you start closer to the solution that you want to approximate, and so somehow the optimization process will be easier if you start from a guess that is not so far from where you want to go. Yes?
Is there a condition of orthogonality and normalization?
So I'm guessing those are orthonormal because they come from a Hartree-Fock calculation. So, but then I don't think there is an orthonormality condition in this, but this is picked up by the variational Monte Carlo method. And I'm guessing that maybe in practice there are some renormalization appearing at some points to kind of ensure that the wave function doesn't doesn't explode or doesn't go to zero everywhere. Yes.
Why do we go for equivariance rather than invariant?
This I'm not so sure, to be honest.
Maybe with the Slater impermanent.
I'm guessing that this is because it's somehow more general than invariance, and then you keep the antisymmetry at the end, so you're fine.
Another question. So here, if you wanted to train this, you will do an expensive training to get one single wave function.
Yes. It's not, I mean, but you expect this to be less expensive than solving the Schrödinger equation. So I think that's and since Schrödinger equation is so expensive, this is not so expensive at the end. I mean, here you still do like a Hartree-Fock calculation at the beginning. So you can see that as a kind of a variational Monte Carlo post-Hartree-Fock method. Yes.
The point though with these methods is that they are ab initio. So the only thing that we require is the minimization of the energy. We don't have a training data or something.
No, we don't have training data here. Yeah. So yeah, that's a very big difference compared to what I presented before for the energy, where we have reference data, which is DFT. Here, we just want to minimize some cost, and the cost is our energy.
That is going to work for the ground state, right?
Yes, in that case, it only works for the ground state. Then if you want to go to excited states, I'm not sure how you would do. Yeah. Here? Yes. So
with respect to xi. So in the backflow, usually with the backflow, the new orbital is a modification of depends on the electron, but
yes.
also on the modify also the dependence with respect to the electron charge. Okay.
Yeah. Okay. So I think I see what you mean. So. I mean, I think these can really be included in the framework, like the generic framework, where you say that the orbital depend kind of as the main thing as the xj and then all the xk. And here, I mean, for this would just be somehow some kind of p tilde of this variable. And then this phi tilde is a function that only depends on on R3, whereas this is a function on R3n. So this is kind of the difference between those two.
We get ratio like you can like 5
Yeah.
And just multiply by the ratio of the of the divided by E of its I. That's different. The term in factor, which we cast it as in great. And the term in factor of the I that 25 for the I depends on I. If you try to work out the usual that factor I mean in this language, you can have the same expression, but it seems that the multiplicative factor F.
Oh, yeah, okay. Now I think. Yeah. Okay. Yeah. But you could still have. I mean, you could still have something. You could still choose to parameterize this with an xi as well. Just different choice of parameterization. Then you have to see if it works in practice. In this work, I believe they didn't. Yes.
So with this method, you don't get the normalized wave function, right? You only get the wave function up to the, so, and if you want to compute an average value of an operator, you still need to normalize the xi that you generated within the value.
So I don't think the normalization is a problem here.
PMC is automatically normalized.
Well, in the Monte Carlo, yeah, but so then you need to keep this xi that you generated with the VMC if you want to compute something else than the energy with this wave function.
Yeah, I don't think normalization is a problem in this context. But this has really to do with like a standard variational Monte Carlo method, and I'm not really an expert on that, so leave other people speak about that. But yeah, so
Yeah,
I don't
know,
think. Yeah. Okay. Okay, so this is for the Paulinette, and then I would like to discuss the Ferminet. So Ferminet has been proposed more or less at the same time as the Paulinette. So there is a first paper by Paul and co-authors in 2020. So this were mainly people from Google DeepMind and also one person from Imperial College. And so it's here there is no Jastrow factor, but it's a backflow, and that's in the generalized sense, let's say. So what they do is that, so they write the parameterization of the wave function as a sum of generalized ladder determinants. And so here, so I write it like this. So phi1 x1 x, so I write it x not 1, etc. Phi np x1 x not 1, and then and so on up to phi 1p xn x not n up to phi 1 phi np xn x not n. Okay, so this will be weights that can be chosen. Okay, and then the way they define, so then in this parameterization, one only needs to see how they parameterize these generalized orbitals. And the way they do that is basically they define some kind of neural network of some variables, and then they put that in another neural network. So I'll write this down. Yes, yeah. Yes. Yep. Okay, and so here, so what we have is that, so we first define kind of a collection of features that are defined as some kind of neural network that depends on the quantities. So basically xi minus RK. So here the RKs are the positions of the nuclei. So that's the correlation for K. With both the vectors and the absolute the norms. Then some xi, and then the kind of the same thing, but within the electrons. So they define those variables. Same thing with the norms. Okay. And then they define the phi I p of xj x not j as some kind of weights WIP times xjl plus some weights times sum from k equal 1 to some number m WIKP exponential minus a IKP xj minus xk. And so here there are a few parameters. So that means here we have hidden here many parameters that generate the neural network. And then when we define this quantity here, we have the weights here, the biases here, and then we have other weights here, and the A's are also parameters to learn.
The capital X the same as capital R.
So because the capital X is the output of a neural network.
The last.
Oh no, sorry. No, yeah. That's the
Same capital X.
Yeah, it's the same capital X. It's just that they write it as some kind of vector. So but that should be the same.
What is the capital R?
Sorry. The capital R are the positions of the nuclei. So basically, you take a neural network. You somehow define kind of basic descriptors that are based on distances between electrons and nuclei and electrons and electrons. And so you take two different things, which are the differences of vectors and then the sum of the norms. And then those basically will have the right symmetry. Then you build a neural network with that. And then with this neural network, you have the somehow features. And these features, you put that in this complicated formula.
In this case, they don't have to start from R34 or something because
exactly. In that case, they don't have a dependency in another method. So, but then how to explain the choice of this? This kind of parameterization. Then I don't really know. Yeah, sure.
So we showed, or let's say we trust that the backflow is a complete ansatz.
Yes.
But with all these parameters that go into the orbitals, is the minimization in the end well defined or over defined or undefined?
I mean, I think the parameterization, I don't know. So I mean, it's probably the problem is highly non-convex, so a lot of bad things can happen, let's say. The thing is that I'm not sure that this parameterization is complete. So it's complete if you say that you generate all possible orbitals, generalized orbitals here. But since here you choose a specific parameterization, I cannot say. I mean, it may be complete, but I don't know. Okay, so apart from Paulinet and Feminet, which I would say are the most used method in this field, so there have been other methods that have been proposed, and so a lot of them are based on variants of these Jastrow or Jastrow backflow ansatz. Maybe to mention just another one, I mean, two other methods. So there is a method called deep wave function, which has been proposed in a little bit before that, actually, in 2019 by Han Zhang and Wein and E. And so here they do, the ansatz is a little bit different. This is why I want to mention it. So it's a Jastrow type ansatz. But they don't use latter determinant, they use products of antisymmetric functions. So what they do is that they do some kind of Jastrow factor, and then they write a product of some antisymmetric function that only depends on two variables, and then they consider the product for E less than J. Okay, and then there are also works where they so a lot of these machine learned wave functions are actually inspired from spin systems, because it's kind of easier to parameterize things for a spin system. And so there is actually one work where they explicitly use what they did for a spin system. And so this is a paper by Chu, Metze, Capo, and Carleo. So what they do is that they basically map the configurations to an equivalent spin system. Then they use everything they did for the spin systems, and then somehow they go back. So that's another thing that exists. And so maybe to finish, I'd like to mention another work that has only been published in for 1D systems so far, but which is based on ACE. So so it's a I would say I don't remember the paper, so it's probably Ordner 2 edition 2024, something like that. And so here what they do is that they use a backflow, and so so they don't use the Jastrow factor, and here they use So the wave function is parameterized as a determinant of the phi I x j x k k not j. So exactly as before. And then the way they parameterize this is they say that it has to be completely symmetric with respect to the permutation of these variables. And so for this, we can use the atomic cluster expansion. And so in a bit in a similar fashion as the people from Schnet developed the Paulinet. So all the features that need to be invariant, then you use what you have done for the interatomic potentials. And so here, what they do is that they write this as a product. So they kind of extract a one-body function for the, so that would be maybe chi of xj, and then there would be a product. So then maybe I write it abstractly as somehow an atomic cluster expansion of the other variables. And I'm not sure this is in their paper, but I believe that this can be proven to be complete, because ACE is complete in the space of symmetric functions. And so probably maybe at the cost of having several functions here, then this would be complete. And so what they do is that then they have the parameters that come from the ACE, and then they do similarly as the others, stochastic gradient descent to optimize the energy of the wave function. And apparently, so I mean, then you can wonder whether you can use maze, for example, and it seems that it's possible, but has been proven to be hard in practice to kind of optimize, because at some point you get so many parameters that like optimizing is getting difficult. Okay, so I think I have finished what I wanted to say on the wave function. So I don't know if you have any questions on this. Yes.
Think of a similar strategy in orbital space. So of course we manage some features, but let's say we have a fixed atomic orbital basis, and we could optimize like configuration interaction coefficients, or is this done also in the literature?
So you mean optimize configuration interaction coefficients with variation on Monte Carlo?
No, but using neural networks.
Oh, you mean so the thing is that when you have configuration interactions, your problem is linear. So I would say that since you have the equations that are explicit, it's better to just write them explicitly and solve them explicitly. I mean, solve them. Mm-hmm. So yeah, maybe, but I'm not aware of anything like that. Yeah, the thing is that I don't know, to be honest. Yes.
These approaches, do you expect to be better than, for example, couple cluster methods in accuracy, or do you just in terms of computational power?
So this I don't exactly know how they compare. So I would say that it highly depends on two things, which are the ansatz that you use and the optimization. So one the one difficulty when you use stochastic gradient methods is that it's very difficult to converge to global minima of the energy. So finding the global optimal on the parameters is very, very difficult. And so in general, so if you go to, so for example, you will never be able to reach machine precision in terms of accuracy if you want to solve this optimization problem, even if the ansatz would be complete. Because basically you get stuck at numbers like 10 to the 3, 10 to the 4. So that's one thing. But then if you want to reach just chemical accuracy, which is about that, then it's not, to me, it's not clear whether you, I mean, in principle, it could be Kappa cluster, but I don't know how it compares in general. Yes.
So I don't think you can really compare, but it's not the same way.
Yeah, sure, but I mean, in the end, you can still compare the energy and see whether.
You can compare the total energy will be hardly.
Okay, yeah, but I mean, there are things that you can compare. So yeah,
Sure.
so then you can see.
I think the main question is that can you actually compute energy differences with those approaches? Because if you do so the good thing about complex cluster is that if you do the calculation of the molecule and the atoms, you take the difference, you make it very good. But here, because you're never quite sure where you are the two or whatever, if you start having errors on the atoms and the molecules, you probably know the difference.
Yeah. Okay, so to continue, I would like to mention a little bit how, so that's for the wave function, but I wanted to talk a little bit about learning Hamiltonian. And so and especially, I mean, everything that's related to learning equivariant properties or equivariant quantities. So the thing is that, so the energy is invariant with respect to rotations. Then the forces are equivariant, but in general, they are always computed at the derivative of the energy. So we don't really fit the forces directly as an equivariant quantity. But then, so one thing we can try to learn is the Hamiltonian in some chosen basis. And so if we use localized orbitals, then the Hamiltonian will be equivariant. And so then one can wonder how we can learn it. So here the idea would be that we have, so here we recover the dependency in the nuclei, and so the idea would be to compute the truth, I mean the Hamiltonian in some basis for many configurations, and then you want to predict the Hamiltonian when you have a new configuration. And so this you can, for example, use to avoid all the self-consistent field iterations that you have to do to solve, for example, DFT problems. Okay, and so if you look at, so if you take the Hamiltonian in a localized basis, what you have is that you will have a given number of orbitals for each atoms, and so the Hamiltonian will look like something like this. So you have blocks that correspond to interaction. So then you have two typical different blocks. So you have let's say the blocks on the diagonal will be treated differently than the block that are off diagonal. And so what happens is that okay, so in general, so if I just look at an element in a given block, so here, okay, I put the dependency in parentheses because I already have two indices, but that's basically some basis function KAHKB. And so then if so here what is typically used are radial basis functions times spherical harmonics. So here if this is G, some G of R times YLM of R hat, then if I take if I look at what happens to some block of the Hamiltonian when I rotate the configuration, then what happens is that I will get some Vignodi matrix on the left and on the right, because I have these two spherical harmonics that will be modified. So, for example, if I have let's say Aj and I consider the 0, 0, then this will be so invariant. So I will just have the same thing with so basically some coefficients in the Hamiltonian will be invariant, some will be equivariant with different Vignodi matrices. And so you have to consider all the blocks in the Hamiltonian a bit differently.
Capital I and J are for the Hamiltonian in the CI basis, and the small a and b.
So the A and B is for one particular basis function, and the IJ is basically an atom. And so you have a collection of atomic orbitals for each atom. Yeah. So yeah, in that case, it would be like for DFT or yeah, typically DFT. Yes. And so here, so this is valid for so this is also the case for her diagonal blocks. So this doesn't change. What changes is the invariance with respect to the permutation. So basically here, if we have the diagonal blocks, so what we are looking at is so we have one center atom I, and we have atoms around, and so what we need to predict here to predict the II block is a function that is really kind of similar to what we had before, in the sense that we have the environment of an atom, and then we can use any parametrization that we had before for learning such an environment. Yes.
The property when you have this kind of wave function by element. times the function of
Yes.
pressure.
Yes. I think, yeah. So then now, when we look at offsite blocks, so the Hij. So what happens here is that we have two atoms, I and J, and somehow we don't have the environment of an atom to consider, but the environment of a bond. So somehow we have a bond here, and we need to consider the environment of this bond. And so basically the permutation invariance will be only with respect to the other atoms. And so possible parametrization for this is therefore to kind of separate this bond here, and then to consider the middle of the bond as a reference point to kind of consider the rest of the interactions with the other atoms. And so a way to parameterize this Hij of R would be to consider this kind of some function that depends on Rij, maybe small Rijk, which would be the vector from the center of the bond to the atom K, and then this can be no, sorry, I have a little problem here. Something. Okay, no. Okay, sorry. That's okay. So here we can define two types of I mean one function which will be some kind of edge function, which is something that depends on the so the vector between the center atom and the so this would be some K here, and then we can parameterize that as a radial function times spherical harmonics times some cutoff function. And here somehow the cutoff function depends on both the atom I and J. So Ri, Rj. And then if we want to construct function that satisfy the right symmetries, then we can consider, for example, things like, so we first consider a function that only depend on the bond vector, so Rj minus Ri, and then we multiply this by let's say any symmetric function of the Rijk, and so this could be, for example, a product of functions based on this so something like product from T equals 1 to nu of some, so the density function that would be based on this edge function. So this would be here sum over k of this phi and Lm E of R I J K. So this would be a possibility to account for both rotation equivariance and also the fact that we now have to deal with the environment of a bond instead of the environment of just an atom. Okay, so that's something one can do for the Hamiltonian to kind of speed up calculations. Then, I mean, there is always the question of kind of the exact parametrization and then how the training is done and the optimization is done. But so this is also something that can be interesting in some contexts. Okay, so to finish, so maybe a few things. So so far I only talked about like a single species systems to simplify kind of the notation and so on. So in that context, if you want to look at multi-species systems, what you often do, so I checked that yesterday, so you mostly consider several densities, where you would consider the density for the different atoms, and then you would correlate them. So that's one thing. And also maybe another point, which is that when we consider a density, so saying similarly as in the power spectrum and so on. So we had something like rho r of x, which is the sum over I of gx minus ri. So in what I presented, I had basically one example with a Gaussian function, and then one example with a Dirac function. So those are two very localized functions, but so there are papers where people actually use like more slowly decaying densities to kind of account for long distance interactions. So typically, if you put like a Coulomb or something like that, then this will decrease way slower, and then in principle you can account for like more long distance interactions if this is what you're interested in. And also, so I talked a little bit at some point about the different data sets that were out, and I forgot to mention two very recent data sets. So basically, one is from Google and one is from Facebook. So they they have a lot of computer power, so they run many simulations, and so there is the one data set. So both are from 2015, so very recent. And so there is the QCML data set, and so they run basically 33.5 millions of DFT calculations. And I haven't checked the details, but I'm sure that these are big calculations. And so the very recently, which functionals? So I don't know on the top of my head, but so for the other one is called Open Molecule. And this is so this one is from Facebook, and this is 100 millions of DFT calculations. So And here I think they do that in, I couldn't, I don't know about the functionals exactly, but yeah. So I'm guessing that they expect these to be used as a very big reference calculation. Yes.
Type of systems was.
So I would say more or less everything. So I would have to check, but I mean, for open molecules, I guess it's kind of only not molecules and not materials. But yeah, I guess that I think really the main idea is that they want to build like models that work for everything, like a kind of just one model for all application.
Also research centers doing that? You don't know that.
Yeah, that's true. I don't know where they're based, but yeah. Sorry? That's possible, yeah. That's yeah. Okay, so I think that's everything I had to say. So thank you very much.
Now you deserve a little present.
Thank you. Wow, thank you very much.